potential energy of a dipole in an external field. So in our previous chapter we have discussed that if a dipole of magnitude suppose minus q and plus q and the dipole length is 2a, if it is placed inside an electric field, then it will experience zero force, the net force will be 0 and it will experience some torque, and the torque expression will be your P cross E, where P is the dipole moment and E is the field. So suppose an external torque will be applied in order to rotate this dipole against the torque, and it has been supposed to be rotated from angle theta naught to an angle theta 1. So theta 1 must be this one. So if I want to rotate this dipole from this position to this position, that means from theta naught to theta 1, against this torque I have to apply some external torque, and let us find out what is the work done by that external torque in order to rotate this dipole from this position to this position. So the work done will be, we know that integration of work done will be our tau into d theta, and this tau is our external torque. We have to apply some external torque against the electric field in order to rotate from theta naught to an angle of theta 1. So this tau will be P cross E into d theta. So this tau, this will become Pe sin theta into d theta, and the limit of theta will be from theta naught to theta 1. So I will write the lower limit theta naught and the upper limit as theta 1. So here also I will write theta naught and this as theta 1. So P and E, we know it is an uniform electric field, so it will be constant, and this P is also constant. So PE, let it take out from the integration. So we will now have theta naught theta and sin theta d theta. So the integration of sin theta gives us minus cos theta, and this will be your P, and limit will be theta naught to theta 1. So if I will put the limits in this equation, I will get PE is equals to, I am doing it directly, that will be cos theta naught minus cos theta 1. So this amount of work done will be stored as potential energy. U is equals to Pe cos theta naught minus cos theta 1 if we are rotating the dipole from an initial angle of theta naught to an angle of theta 1. If we want to find out what is the potential energy of the dipole inside this electric field, then what we can do, we can choose a position where the potential energy is taken to be 0, and that is when theta naught will be equals to pi by 2. If I will place this dipole 90 degree or perpendicular with the electric field, that position will give you 0 potential energy. So theta naught, let us take theta naught is pi by 2 and theta 1, theta 1 we say theta. So what is the potential energy of the dipole making an angle theta with the electric field? So what will be the potential energy of the dipole if it is making an angle theta with the electric field? So let us put the values. U is equals to Pe. In place of theta naught, I will put pi by 2 cos pi by 2 minus this. In place of theta 1, I will write theta cos theta. So this terms become 0, cos 90 0. So now I will have minus Pe cos theta. I can simplify this again. We know that the cos theta terms we can write as the dot product of these two vectors P and E. So this will be the expression associated with the dipole making an angle theta with the electric field. Now I can go for three cases. One is stable equilibrium. So when we will say that this dipole is in stable equilibrium, now if the theta is parallel to the electric field, that means the dipole P and E, if they are parallel to each other, that means that will be U is equals to theta will be 0. So the expression will be simply minus P E. So this will denote us the stable equilibrium case. And what is unstable equilibrium? Unstable equilibrium will be when theta is equals to 180 degree. That means when it is anti-parallel to the electric field. So unstable equilibrium is when theta is equals to 180 degree and U will be at that time your plus P E. Because we know that if a body is having minimum energy, that will be in stable state. So we are saying that it is in stable state since we are having a negative sign. Here we are having maximum energy. So it is a case of unstable equilibrium. Then another one is zero energy. Zero energy when theta is equals to pi by 2. So U will be equals to minus Pe cos pi by 2, which is equals to 0. So this is regarding your potential energy of a dipole in an external field. You can do it in another way, or you can find out the energy by using the energy expressions or using the expressions of potential. So go through this, and our next topic is electrostatics conductor. Electrostatics of conductor. So I will discuss few points which are in your book. Electrostatics of conductor. So before going to the topic of capacitor, which is actually a conductor, we should know about these things. So electrostatics of conductors. Your first point is that the electric field inside a conductor, the electric field inside a conductor is equals to 0. If there is a conductor, then the electric field must be 0 inside it. Second point is that, as we have discussed in previous class, that the electric field must be perpendicular. The electric field must be normal to the conductor. It should be normal to the surface of the conductor. Third point is that since electric field inside the conductor is 0, so according to Gauss law, we can use our Gauss law. Since electric field E dot S is equals to Q by epsilon naught. Since electric field inside the conductor is 0, so no charge, excess charge will reside inside the conductor. That implies that charges will remain only at the surface of the conductor. Fourth point is that the potential is constant throughout the spherical conductor and also inside the conductor. V is equals to constant, means it is whatever it will be at the surface, it must be equals to inside the conductor. If potential at the surface of conductor is V, then it will be equal inside the conductor also. So whatever the potential at the surface, if it is of 10 volt, then inside this we will have the potential 10 volt. Next point is that if we are going for the surface of a conductor, then the surface of conductor will have electric field is equals to sigma by epsilon naught. Means sigma is the surface charge density and the magnitude of electric field must be equals to sigma by epsilon naught at the surface of the conductor. Last point is sixth point. This one must be 5. Last one is electrostatic shielding. Electrostatic shielding is a phenomenon where inside the conductor or inside the cavity of a conductor there will be no influence of electric field. So sixth one is electrostatic shielding. Shielding effect means the cavity inside a conductor. If you are having a conductor and you are having a cavity inside the conductor, then this will be shielded from the outer influence. If you are having an electric field, suppose at the surface or any external electric field, then there will be no effect inside the cavity of the conductor. So electric field inside the conductor, inside the cavity will be again equals to 0. And this phenomenon is known as electrostatic shielding. So this phenomenon, that's why the phenomenon of electrostatic shielding, one example is during thundering or lightning, you are advised to sit inside a car. So you will be shielded from the outside surface or outside surrounding. So these are the important points regarding electrostatics of conductors. You go through the book and next class we will discuss about dielectric polarization. Thank you, students.